Okay, welcome back. Again, all I want to continue with is some work in electrical engineering. Okay, and again, we're looking at motor field windings and configurations. Now, let me just go back so that we can recap what we were looking at the last time. Okay, I'm not going to take too long on this because you can see this is session motor principles 5. This will be motor principles 5. Okay, well, let's just say session 5. Sorry, I'm trying to get my teeth in. Okay, and this you've covered already. Okay, so all I'm doing is just going back as a recap session to let you know that all this is linked. Okay, okay, let's go down. Okay, now remember, you need to write these out for yourself so you understand the concepts behind this. Okay, and as I've said, this gentleman does some very good work. Okay, but some of the answers can sometimes be incorrect, so you need to work it out yourself. Okay, and we went through that one already. And here's the self-assessment. Now, these answers here may be or may be correct, but some of them are not. So it's important that you apply the relevant formula, extracting the information that you need from the question so that you arrive at the correct solution. Now, also make sure that you have the correct Newton meters or the correct units when you're giving your answers, okay, at all times. Now this is the answer. Now don't bother to adapt the view that, oh, you've been given the answers already. You did not work out these answers, right? So you don't know if these answers are correct or not. It is down to you to ensure that you have applied the formulation and arrived at the same or similar answer. If the answer does not come out the same, then we can write to the guy and say, well, look, you gave an answer to a certain question and it wasn't quite right. Can you tell me what I did wrong, basically? So you can ask a question of Mr. Dunn, okay, or his company. Now again here, I won't be doing this for you. You will need to do this for yourselves as the answers are quite clearly given, okay? Look at the applications, learn from that. Okay. Right. What I want to look at now is something called shunt motors, okay? Shunt motors, all right? Now, in this case, the field winding is connected in with the armature as shown. The field current, constant to flux, theta cannot be changed except changing the supply voltage, and so is regarded constant. Let me run that again. My apologies, I missed a bit. In this case, the field winding is connected in parallel, okay, with the armature as shown. The field current is constant, so flux theta cannot be changed except by changing the supply voltage, and so is regarded as being constant. Okay, now again, this diagram you should be drawing up, because that's the internal resistance, that's the field. Okay, and again, EA equals V minus IA RA. Okay, and again we have T as torque in regards to force, newtons. Okay. Now I'm not going to read over this because you've looked at this already, and I've given you information prior to this already. So let's make sure we get everything in view. Okay. Okay. Now in this case here, theta is constant, so everything is a constant except T and N. For constant electrical power, it follows that T equals Cn minus Cn. Sorry, T equals C1 minus C2N. This shows that at zero speed, the starting torque is C1, and as speed increases, the torque drops off. The ideal torque speed characteristic is as shown. In reality, the line is curved down due to other effects not considered. Okay. Now, what we're going to look at here is a work example. A DC motor is shunt wound and is supplied with 400 volts. The armature resistance is 1.2 ohms, and the field winding has a resistance of 300 ohms. When running with a torque of 70 Newton meters, the motor takes 19 amps. Determine the speed of the motor, assuming the electrical power is converted into mechanical power with 100% efficiency. Now, you need to write this out so you understand the formulation behind it, and you learn how to apply the formulas to bring it to a positive conclusion. The field is connected across the supply. The current taken by the field winding is current field equals 400 over 300 equals 1.33 amps. Now why 400? Because 400 is the supply voltage. Why 300? Because I equals V over R, therefore I equals 400 over 300, and your 300 is here. Okay? That leaves you 1.33 amps. So that's the current you know is in your field. It's in your, field windings. Let me try and make sure that I don't shorten it for my own edification. Okay. Now the current taken by the armature is hence 19 minus 1.33. Now the motor takes 19 amps. That leaves you 17.66 amps. Now EA equals V minus IA RA equals 400 minus current taken by the armature times 1.2. Now 1.2, where does the 1.2 come from? It's the armature resistance, okay, and that is here. Ouch. Okay, and that gives you 378.8 volts. Now check that for yourself, because sometimes it doesn't actually work the way you think it does. And let me just see something from here for myself. Okay, now be sure that you're happy with your answers, okay? And yes, I'm just doing a little working up myself to make sure that what I'm looking at is relevant and that the answers are correct. So yes, I'm doing a bit of calculations myself. But it's important that you apply these calculations for yourself and do the examples given. Work out the examples, write them out, get them done, okay? I'm not going to spend any time on that now further, okay? And again, here is further examples. Work example number 5. Now again, to give you the solution to the question and the process, you need to make sure that you are applying the formulation that is relevant in solving the question, okay? Get used to doing that. I'm not going to be doing this for you now. At this level, you'll be doing this work for yourselves, basically, okay? And for me, my first question here is, where did you get 15.21 from? That's just my own question. So the question still stands, as he has related this to the previous question, okay? So keep that in mind and read the information given, okay? Again, here you have work example 6. Again, I'm not going to go for this with you. You will do this for yourselves, okay? Now, by working through these things, it enables you to get a better understanding of the working that you need to do and how to apply that principle. Okay. And again, this is session 5 in regards to motor principles. Session 5. Okay. Compound motors. And that is not interesting. Compound motors. The compound motor is a cross between the other two with both a parallel and series field winding. For constant electric power, the torque speed characteristic is between that of the other two. So again, you draw these diagrams out and you make them your own business. You draw them out. Okay. You're then looking here at your self-assessment. Okay. Yes, I know we've given you the answers, but that does not mean to say you do not apply the principle and formulation to arrive at the answers. Make sure the answers are correct. Do not make an assumption that they are. Starting large DC motors. Okay. Now here, what I'll be looking at here is starting large DC motors. Because some motors are quite large, and believe me when I tell you that they will take quite a bit of power to start up. And these would normally be 3-phase motors. Consider a basic DC motor. The terminal voltage is V. The back EMF on the armature is E. The armature resistance is RA. The field resistance is RF. The flux per pole is theta. Again, I call it theta. You can call it something else. I may have it totally wrong, but whatever. It represents the flux. N is the motor speed. From earlier work, it was shown that V equals EA plus IA times RA. Now again, you are applying the formulation that you've done previously. So this process becomes a work in practice. And practice makes what? Practice makes perfect. Okay. Again, here is for you to look through, and I'm not going to. These diagrams here, you should be just drawing out each one. Draw it out on a full A4 size paper. Then you put it. In order to limit the current, it is normal to insert a variable resistance in series with the armature, which is gradually reduced as the motor speeds up, and then latched in place in the zero resistance position. In the event of an interruption to the power, the starting resistance is unlatched and springs back to the starting position. We should consider how the starting resistance is used with different motor field configurations. The 3 types of configurations are shown below. Okay. You have series motor, shunt motor, and compound motor. Okay, and in each case, series motor. In the case of series wound motor, the starting resistance is placed in series as shown. Okay, and it shows you where the resistance is. Okay, and then let me just make sure that I am pointing to the right place. Thank you. Yes. Shunt motor, okay? In the case of a shunt wound motor, the starting resistance is placed as shown so that the field is initially connected to the supply, and the armature is in series with it. As the motor speeds up, the field resistance is gradually increased and the resistance in series with the armature is reduced. Compound motor has a starting resistance as shown, okay? And here's your compound motor, okay? Showing your starting resistances. Now identify which of the diagram shows a series shunt and compound wound motor. Okay, simple enough. Okay, nothing difficult, too hard. That's a simple case for you to do. Identify which torque speed graph represents series and shunt wound motors. Okay, look back at the work we done earlier. This is session 5 now. Okay, so sorry about that. Just having to move paper out of my way. Slightly. So sorry about that, whatever that was. Okay, now I'm not going to go into generator principle with you. At this level, you should know this yourselves already. You'd have done this in level 1 and level 2 and level 3. Okay, so construction of a simple generator that you know already, and we've looked at this previously. Okay, let me just make it a little bit bigger. Let me just make it a little bigger here, just so I can bring it in so we can see in each case. Okay, so I can bring it in for you to see for yourselves. Okay. Okay, so you can use this yourself if need be. Okay. Now let me come down a little bit as well, and I'll come across, and I'll bring it back to normal size in a moment. Okay. This is just to show you the rotational effect of the conductor in the magnetic field. Okay. As you're cutting through the magnetic field, it's producing a induced voltage. Okay. Let me go down here a little bit. Let me just see what I can pick up with him before I put it back to normal size. And this is your sinusoidal waveform. Okay. So this is not a sinusoidal waveform. It is half wave form. Okay. It's producing a voltage. As a matter of fact, it's producing a DC voltage. Okay. On smooth DC voltage. Okay. To smooth DC voltage, you will need to apply a capacitor. Let me just drop it down a bit now so I can get back to my normal size. 1 second, bear with me. Okay. Okay, let me bring it up a little bit. Okay, yes, I can do that. Okay. Let me just make sure I've picked everything up that you can see, and that's what we need to have covered for today so far. Okay. Okay. Thank you. Okay, good. I'm just making sure that I've covered the bit and that it's clear, because I sometimes go adrift when I'm trying to think of something else on here. Okay, so just to make sure that it is in view. Yes, DC generation. Okay, this is a half wave DC generated waveform. Okay. The smoothing has not taken place because there is no capacitor in the circuit. So this is just a unsmoothed DC rectification. Okay. This is this here will be your sinusoidal waveform. Okay. Positive to negative. Okay. Okay. So again here, it's quite clear telling you what it is and how it has been produced. Make sure to read a simple generator may be produced by rotating a simple loop. Okay, so you read join, make sure you follow the pieces across, the wording across, all the way across. Okay. This, I quite like this, I must admit. It's interesting to how by actually splitting the commutator, we are actually able to produce full wave rectification that uses up both half cycles. Quite good. That has always amused me, actually, I have to admit. Okay. Right, if many loops are used, the rotor becomes an armature. The split ring becomes a commutator. Each loop is connected to a segment of a commutator. And this is just showing you the segments, so how they're connected. Now what I want to do here is I'm going to make this a little bit bigger so you can view it in full, in a larger scope, rather than having to strain your eyes to see it. Okay, and let me just go into it a bit closer. Okay, you can see the flux. Okay, and these are your loops of cables, windings, if you like. Okay, let me just move this over a little bit so we can get the other illustration in. And this is just showing you the commutator brushes. Okay, and how this is now giving you practically full wave rectification, basically. Okay, let me just drop this down a little bit. Okay, let me just go back. Let me just bring him up. 1 second, bear with me for a second. Let me just look at this so we can see this more as well. And remember, this is now your motor. Okay, and now your motor. Okay, and this now shows you how the windings and the armature and the field coils are located. Okay, and this is what purely a representation as to what it might look like. Okay, okay, let me just shrink this down again And let me see if there's anything further I need to look at that I need to bring to your attention first. 1 second. No. Okay, for do, I will come back to it, but let me make sure we get this down. Okay, dropping down, dropping down. Okay, I'm dropping down further. Okay, and that will be it for me at this point. Okay, that's good. That's good, that's good. Right. Now this is for you to be able to read for yourself. So let me just go back and make sure that we can get it all in place and that you can read at your leisure. Now you do have the facilities to zoom in. Okay, and let me just go back a little bit further. Okay, we'll pick this up again further. Okay, and I'll stop there. Okay. Okay. Okay, good. Good. Right, now, theory section. In theory, the EMF generator is E equals BLV. Now, you are level 4, so I'm not going to spend any time on this. This is for you now to follow up on. Okay? And, PyDN. Yeah, remember doing these in class. But here's where you will now have to come in and apply them yourselves, okay? Nobody is going to do this for you. You have to know how to do this for yourself and apply it. Okay? Okay. Okay. Now, this is for you to do your own self-assessment and generate the configurations. And here is where I want to actually enlarge each one of these so that, let me give you the print first. Let me just see if I can make the print bigger first. 1 second. Now I'm not going to read this print to you. This is for you to read yourselves. But let me just see if I can bring this print to my, is it, sorry, it's a little bit large. So let me just go back a bit, okay, and bring it into view. Okay, and let's make it bigger. I'm going to make each of these bigger so that you can see it. You don't have to be pondering as to what you're looking at, okay? And down here you can see the armature resistance, brushes, etc. Again, load resistance, okay? And let's just get this up and over, and we look at these in turn, okay? Let me just bring it up a bit bigger so we can see it without any, okay? And here you have your types, and here you have separately excited, okay? Okay, you have here the shunt, okay, motor again, okay, and again here you have your series motor, okay, and here you have your And here you have your, sorry, something I must have left on the sheet. Okay, your compound. So going across, okay, and then just coming across. So let's go across again, thoroughly, so you can see them for yourselves, okay? I'm bringing it to a close there. Let me just drop this back down to normal, okay? So we can then see all that we need to see, okay? And this is quite educational and important information that you have in here. Make sure you follow these up and you write out the information for yourselves. Okay, now here with this guy's work, it does give me a few permissions, okay, and it does allow me to do this, okay. So as long as I have not made any changes to his work itself, which has not been done, it's purely being utilized as a learning platform only, okay. Shunt rounds, series round, okay. Now compound round, okay, etc. Now let's look at this a second here a minute. I'm just going to here. I don't want these to be too out of focus. Okay. Okay. And here, ladies and gentlemen, is where you can begin to test yourself. Okay. And I would strongly suggest that you begin to do that. The more practice you put in, the better you become at this type of calculations. Okay. And this will be it, right? This is session 5, motor principles. Okay, that I'm just referring it to as motor. I call it motor principles. Okay, let's just go back slowly and make sure we get everything into play, and we'll play this all the way up to the top. Now again, pause, expand the work, zoom in, extract the information, utilize, get familiar with the method of calculations and using the formula. Know the various types of motors available, or the various types of configurations, I should say. Okay. Okay. Okay, thank you. I hope you found this useful. Have a good day. Bye bye.